Welcome back to Science Simplified, everyone. Today, we're diving into the fascinating world of renewable energy, specifically hydrogen production. We all know how crucial it is to find cleaner alternatives to fossil fuels, and hydrogen is a promising candidate. But creating hydrogen efficiently and sustainably is a real challenge.
That's right, Sally. And that's where today's research comes in. We're discussing a groundbreaking study on accelerating the optimization of metal and ligand combinations for what's called light-driven hydrogen production. Think of it as using sunlight to create hydrogen fuel, a truly green process.
Exactly. This research tackles the huge problem, finding the perfect recipe for this process. It involves a lot of different elements working together, metals, ligands, and a photosensitizer that absorbs light to initiate the reaction. Traditional methods of finding the ideal combination would take years.
Years, indeed. This is where their clever use of something called a design of experiments, or DO approach, comes into play. Instead of randomly testing combinations, they used statistics and computational models to design experiments that maximize information with minimal testing, greatly speeding up the whole process.
It's like baking a cake, but instead of flour and sugar, we have different metals and special molecules called ligands. The DO approach helps them figure out which combination of ingredients, in this case, metals and ligands, yields the tastiest cake, or rather, the most hydrogen.
Great analogy, Sally. They use this DO strategy to test 4 different metals: gold, copper, iron, and nickel. They also used a specific type of molecule, a polyethylene glycol, methyl ether thiol, as a stabilizing ligand. Think of it as glue holding everything together, helping the catalyst stay stable for longer.
And to make things even more efficient, they used a high-throughput system, essentially a robot that does all the mixing for them. This setup allows them to run hundreds of experiments simultaneously.
Impressive. And their results? They found optimal combinations for each metal, showing how much of each ingredient, the metal, ligand, and photosensitizer, was needed for the best hydrogen production. The model even predicted the performance peaks for each metal with remarkable accuracy.
Amazing. Not only did they find the best recipes, but they also discovered that a stabilizing ligand is key to maintaining the efficiency of the catalyst over a longer time. The experiments ran for over 45 hours. That's remarkable stability.
Absolutely. They found that the iron catalyst, despite not being considered a noble metal, performed surprisingly well and showed incredible stability in the system. This opens up possibilities for using more affordable and abundant metals, which is a huge win for scalability and sustainability.
So, in a nutshell, this research has demonstrated a highly efficient way to optimize the process of creating hydrogen fuel using sunlight. They combine smart experimental design with automated high-throughput experiments, leading to significant time and cost savings. Plus, they uncovered promising results with less expensive metals, paving the way for a broader and more affordable adoption of this green technology.
Precisely. The efficiency gains, using more accessible metals, and the extended catalyst lifetime are all significant steps forward. This method could be adapted to other complex chemical processes, revolutionizing various fields beyond just renewable energy production.
That's a fantastic point, Matthew. This research is not just about making hydrogen, it's about developing a powerful new way to tackle complex scientific problems. It shows how the perfect combination of smart experimental design and clever technology can accelerate the pace of discovery. Thanks for joining us on Science Simplified today.
My pleasure, Sally. Until next time.